Hello, kids. Welcome back. I hope you are having no doubts and questions when it comes to structural isomerism. If yes, waiting for your messages in the Dropbox. Please do let me know your questions, your queries in the comment box. And for today, let's start and discuss about the stereoisomerism. In this, the key word that you need to write down if the definition is asked, you will write down the same which is there for the isomerism or structural isomerism definition, that is same molecular formula but different structural formula in space. You write down this or you write down the word special arrangement. Any one thing is compulsory. It's the only word that makes a difference from stereoisomer to the simple isomerism, right? So let's talk about the geometrical isomers first. So the geometrical isomerism, again, the word says that geometry is changed. Geometry means the arrangement, the way they are being arranged. Now, any compound that will show geometrical isomerism will have double bond. Double bond what? C double bond O, will that double bond count? No. Carbon-carbon double bond must be there, right? So when the carbon-carbon double bond will be there, what will happen? Because of this double bond, it will have fixed rotation. It can flip like this only, right? If this is there flipping, this can flip only like this. This cannot flip like this because it is fixed by two ends. So because of this fixed rotation along the axis, it is not able to rotate and can flip around like up and down only, right? Now, when carbon is attached with a double bond, how many valencies are left? Two valencies are left. Each carbon, two valencies will be left. Now, if in this particular compound, these valencies, if I name this as X, Y, this is also X and Y. That means there are two different groups. Only two different groups attached, then it will show cis and trans isomers. What do you mean by only two different groups? For example, I have carbon, double bond carbon. Let's say over here I have chlorine. This side I have C2H5. These are two different groups. I should have the same two different groups on the other side. Let's say this is chlorine, this is C2H5. So I have all over two different groups attached to the carbon. So this compound will show cis and trans isomers. Now, how to find out which one is a cis, which one is a trans? The same group, these are the same groups, they are lying along the transversal. This is how you make a transversal along a parallel line, right? So that's a trans format. So what will be the cis format? They will not lie along the transversal, they will lie on the same side. Right? So this becomes my cis form. Clear? Trans lying on the transversal side, cis lying on the similar sides. To show cis and trans, it should have only two different groups attached. More than that will not show cis and trans. Clear? One thing. Now, over here, since they are same group lying on the two opposite ends, they have net dipole moment cancel out. Right? They are equal and opposite, so they have trans format have zero dipole. Why they have zero dipole? Because the dipole cancel out each other. Please avoid writing becomes zero or something like vague answers. The keyword write down cancel out each other. Bonds are equal and opposite, the groups. As a result, they cancel out each other. Whereas over here, they have a net dipole. Because they are not cancelling, right? Since it has a net dipole, this will become polar in nature. No dipole, this will become non-polar in nature. Overall compounds become non-polar. When the overall compound will become non-polar and this is polar, so it will show what type of force of attraction? Dipole-dipole interactions, right? All over compound will also have dipole-dipole and bonds are also having dipole-dipole. Over here, bonds are having dipole-dipole, but overall they are cancelling out each other. So cis form has higher boiling point than the trans form because they show dipole-dipole interactions. So we have learned multiple things over here. First thing, for cis and trans and for a geometrical isomer, it has to have a single double bond. Then in the double bond, if it is only having two different groups, it will show cis and trans. Trans means the one which is there on the transversal side, the same groups. And when they are on the same side, that is the trans group. Then in the cis form, they have a net dipole, whereas a trans has zero net dipole because they cancel out each other. Cis form becomes all over a polar compound, thus show dipole-dipole interactions, which are stronger. As a result, cis compounds boiling points are higher as compared to trans compounds boiling point. Am I clear? Any questions? Perfect. Now, going ahead with the next thing, which is if it is two, it is cis and trans. One is not possible because compound will not stable. Now, if it is more than two, then what? Like I have a compound. Correct? So now I have four different groups attached. It could be three also, it could be four also. So in this case, you will check the priority. Now, how you will check priority? To check the priority, see high atomic number means high priority. right? So now how to check that? So on this side, I have H. Let's break it down. This C2H5, I can write down CH2 followed by CH3, and we'll cancel out one by one. So to this carbon, I have directly attached hydrogen. To this carbon, I have directly attached a carbon. Whose atomic number is high? Carbon. So the preference is this compound, right? Come this side. To this carbon, chlorine is attached. To this carbon, carbon is attached directly, which is having a higher atomic number as compared to chlorine and carbon, chlorine. So the preference is chlorine. Clear? So check from one side, which one is having more priority. Let me give you one more example. Hmm. This side, though, I hope it's clear. It's easy. You will compare directly H and Cl. So this becomes your priority. Over this side, the carbon is attached to carbon and one carbon. Same, cancel. Two hydrogen, three hydrogen. So two hydrogen will cancel two hydrogen. I will have one hydrogen now. Now this carbon is attached to carbon, whereas this carbon is attached to third hydrogen. Now I will compare this hydrogen and carbon. So the preference will be this. So in a nutshell, you can compile and say that start checking from the carbon to which the double bond is there. Then till the point you are getting the similar compounds, cancel. When you get the two different compounds, compare which is having high atomic number, and that's your preference. Clear? Once you get your preference, see in the compounds on the two sides, are the preference lying on the similar side or on the different side? They are lying on the different sides. That's a transversal side. Yes or no? This is the E format. That means if my compound would have been like this, this would be my Z form, right? Any questions, any doubts? Geometrical isomer is clear. This is the point which is common for HL and SL both. Now we have the last isomer, which is optical isomers. Now in this particular optical isomers, this is only for HL. Optical, something related to optics. And when you talk about optics, you talk about mirror, right? You must have studied this in your physics. Now, what is the use of mirror in the chemistry? So we have mirror images of the compounds. So any compound that will show optical isomer has to have optical activity, right? That means all compounds are not optically active. Who are optically active? That has a chiral center. What do you mean by a chiral center? You have a carbon, it has four valencies. All four valencies has to be different. Different four means four. Three different, one, two, three different, and one is repeating with the someone. No, will not work. A, B, C, D. Four different groups or atoms must be attached. Then only it will have A chiral center. That carbon is a chiral center which is having four different valencies, and you represent that by a star and you call that star as an asterisk, right? Over here, one is CH3, one is Cl, one is Br, one is H. All four different. It is optically active. This is a chiral center. It is going to show optical isomers. Two are same, no optical isomers. One thing clear, to find out and figure out which one will show optical isomers, which one will not. Perfect. Moving ahead, let's talk about the compound. So basically what happens, for this you need to show 3D geometry. Now when we talk about a 3D geometry, you know that there are three types of bonds. One bond is into the plane, one is along the plane, one is out of the plane, right? So carbon has four bonds. One is into the plane, one is out of the plane, and two is along the plane. So the bonds which are along the plane are denoted by a solid line. Simple. Into the plane which is there is denoted by a dotted line, right? Into the plane, that means away from us. And out of the plane is towards us, denoted by wedge bond. What is that? That thick one. This. Right? Now, you need to keep in mind one thing. You cannot change the rotation. You have to make it like this is a carbon. You will show two solid bonds like this, dotted bond, this, and edge bond. Now, things that you need to keep in mind. Don't reverse the order. Keep your dotted onto the left, edge to the bottom, and the remaining two are solid bonds. Avoid 90-degree angle making. Student, do these two mistakes. Everything is clear, still you lose marks. Big no, right? Am I clear? Please stick to this. Now, let's say a compound says you have to make show that whether the compound will show optical isomerism or not, right? So I can say this particular carbon, it is having one hydrogen, one bromine, one this, one this. So four different groups. This will show optical isomerism. Now the problem arises, which one I should show on solid bond, which one on edge bond, which one on dotted bond, anything, anywhere. Anything will work. Let's say I'm saying Br on this. I'm showing C2H5 over here. Hydrogen I am showing over a wedge bond, and this over CH3. You show some other rotation, BR down, C2H5, left, right, everything is fine. Till the time your bond order is like this, everything is fine. You made this. This is a 3D geometry. Now you will make a dotted line. What is this dotted line? This is a mirror. Now, what does a mirror do? It is going to rotate. Actually, what happens when a compound is optically active, you throw a plane polarized light. Right? So when you throw the plane polarized light onto the compound starts rotating. Right? Now, it is not rotating like this, like the way it was rotating in the geometrical. It is rotating like this. Why it is rotating like this? Because it is free. It is having all free rotation because of the presence of single bond. Now, which side it will rotate depends which side is bulky. Right? So for our exam syllabus, we just need to keep in mind the rotation. All this used to come in examination before 2025, but let's study it. So the side which is bulky will go down. So let's take it a very simple example. This is, can you see it? Yeah. This is a simple thing. This side is bulky, so this will go down, right? If I put up pressure on it, so this is bulky, this will go down. So it will flip like this. Yes or no? Same thing happens over here. One side is H, another side is C2H5. This is a plane mirror. Plane mirror shows sideways lateral inversion. Remember? So left will go right, right will go left. So this will go down and the rotation happens like this. H will come over here. So this compound is carbon. Br will remain as it is. Hydrogen will come on this side. C2H5 will go on this side. And then my CH3 is over here. Right? Please keep in mind when you switch, you are switching this bond also. Students do another type of mistake. They switch, but they remain the dotted bond over here. No. Groups are not moving. The entire bonds are rotating. Right? Perfect. Now, if you see this, this has gone like this. Is it along how the clock moves? Your clock moves like this. Your compound is going like this. So this is going in anti-clockwise direction. Again, this is not a part. Right. So which is anti-clockwise is minus and the other one is plus. So that means if I rotate this time it will go like this. So it is clockwise. You call clockwise as dexarotatory. Anti-clockwise as levorotatory. Right? Yes. So what we did today is about the entire isomers, which is geometrical isomers, optical isomers, or the type of all the isomers. Please go through it. I'm not adding the questions up to here because then it will be elongated a lot. I'll add a very small question bank, 4 to 5 question practice video also on it. And then you can see that how well you are able to align your question or concept to that particular practice, right? So that's all for today. Let's wrap the today's session. Hope you have nailed it, you understood it, and this isomerism topic feels like a bit more friend now. Keep practicing. Drop your questions into the comment box and let's do it again very soon. Do hit that subscribe button and I will catch you in the next video. Till then, take care and bye-bye. Good night.